Okay, welcome to FRQ number 3, set number 7. Okay. Part A would like us to calculate the initial energy of the system. So, okay, initially the rod is not moving, so there is no KE, so that means ME initial is equal to PE, which is equal to MGH. Go ahead and expand that. So when we get to height, so look here. Okay, so as you can see, I chose to go up to point B because that's our center of mass, and that's what we want to use. So what we need to do is find height. So this length is L over 2 because it's half. And so that would be opposite over hypotenuse, so sine 60 is equal to height over L over 2. And then to solve for height, you would bring L over 2 over, so it would be L over 2 sine 60 equals H. 2 is equal to 2, so it's 2 over 2 sine 60 H. So that means sine 60 is equal to H. So for H, we plug in sine 60. And then just plug that into your calculator. Get 33.95 joules. Alright, on to part B. It wants us to find the angular acceleration of the rod at the instant it is released. So when I think of angular acceleration, tau comes to mind. Tau is equal to the force perpendicular times r. It also is equal to I alpha. Okay, so erase this. Okay, so again, we're going to be looking here. Okay, looking at point B. And so you have your f of g, right? And then you have an f of g x and your f of g y. Now, you can't just use your f of g because that is not perpendicular to your pivot. Right? That is not perpendicular. So instead we need to use our FGX. So let's write that FGX or I alpha. Okay, and then that is equal to mg cosine theta, because your theta would be here. Theta would be here, so that would be 60. So adjacent, so cosine. And then your r, again, the L over 2. And then your I for rod is 1/3 ml squared. And we're looking for alpha. Alright, now we can just go ahead and plug in everything we know. simplify. And then we solve for alpha. Oops. Rads per second. Rads per second squared. It's acceleration. Alright. On to part C. It's asking us, after the rod is released, does net torque stay the same, increase, or decrease, and justify? So, net torque is going to increase. Okay. Now, so let's first set up net torque. Okay, so we established that torque is going to be equal to your FGX times R. Now, as the rod falls, so as theta decreases, f of gx increases. Because think of it this way, so you have this, right? So right now, at this position, you're using the components, and you're using the x component. But as it falls, you're gonna be using just f of g. You don't need to use components, because when it gets to this point, when it's completely fallen, your f of g is going to be perpendicular to the pivot, so you won't need to do components, and that means it's going to be the whole value, meaning it's going to increase. So that is why tau increases, because your f of gx increases. Your r stays the same, but that would cause your tau to increase. Alright, part D wants us to rank the following from greatest to smallest, and these are alphas for, where's this? Okay, it's alpha for point A, point B, and point C. Okay, so alpha A going to be equal to alpha B, and that's going to be equal to alpha C. Now, this is because your theta is the same for all points, and time is also the same for all points. Now, theta over t is equal to omega, and if your omega is the same for all points, that means your alpha is the same for all points. Okay, part E. Okay, so now it wants us to rank omega. So omega A is going to be equal to omega B. It's going to be equal to omega C. And again, for the same reasoning, theta is the same for all points, and so is time. Theta over time is equal to omega, and if theta and time are the same, all the omegas are the same. Okay, same explanation. Okay, part F wants us to rank acceleration tangential, part A, or point A, point B, and point C. Okay, so A tan C greater than A tan B, that's greater than A tan A. Now, this is because when you look at it, these trace out different sized circles. Now, point C traces out the biggest circle, biggest distance. Point B, second biggest, and point A has the smallest, but they all do this in the same amount of time. So this one has a big over same, a bit bigger over the same time, and the smallest over the same time. So this one's able to cover more distance in the same amount of time. This one covers a little bit more distance in the same amount of time, and this one covers the less amount of distance in the same amount of time. Okay, part G. Now it wants us to rank a centripetal for point A, point B, and point C. Now, okay, so A, C, C, A, C, B, oops, and A, C, A. Okay, so when you set up AC, get V squared over R, right? And now, or not now, but we know that V equals R omega. So we can replace this with R squared omega squared over R. This would cancel out. So then you just get R omega squared. Now, we already established that the omegas are all going to be the same. However, looking at this, point C has this big of a radius. Point B is that big, and point A has the smallest. So AC has the biggest radius, AB has, point C has the biggest radius, point B has the second biggest, and point A has the smallest. And since omega is the same for all of them, you're really looking at the differences in the radius. Okay, on to part H. Wants us to calculate the time it takes for the rod to be fully horizontal. Okay, or perfectly horizontal, excuse me. Okay, so I'm gonna go ahead and set up tau, or torque. Alright, so same setup here, this line. Sorry, there's a bug. Okay. Okay, yeah, so same setup right there. Basically copying it. Okay, and so what we want to do is solve for alpha again. So that means we're going to multiply this side by 3 to get rid of that, but that means we also have to do it to this side. And then we're going to divide by ml squared. So that would cancel out. Those would cancel out. So then now on this side, we have alright, you can plug everything in. Okay, and we want to leave theta as is because what we're going to have to do is integrate to find average alpha. So these would cancel out. That's just 1, so you get 3g cosine theta over 4. Okay. So now I want to integrate to get my average angular acceleration. So it falls all of the 60 degrees, so we have 60 there. And okay, so remember your lower bound, or lower limit, excuse me, that's like your starting. So we're starting at 60 and going to 0. And then this is alpha d theta. Okay, and then you can go ahead and just plug in the alpha that we just found. Okay, and then doing your calculus, get 6.078, and that's rads per second squared. Okay, now I need a piece of paper. Okay, so now that we found average acceleration, what we can do is find time. I'm going to use the displacement function, but with angular. I can't remember what it's called right now. Okay, so it starts from rest. Okay, so for this we need to convert. So it's going to be 60 degrees and we want to convert that to radians. So that's pi over 3. So we plug that in here. 1/2, and then we plug in the a that we found. Okay. Now just go ahead and solve for t. And so that is time for the rod to fall all the way horizontally. Okay. For I, wants us to calculate the amount of time it takes the rod to travel the second half of its total angular displacement. Okay. So now we're at 30 going to 0. So t total is going to be equal to t1 plus t2. Move that around and solve for t2. You get t total minus t1 is equal to t2. Alright, t2. We found t total just now. but we still need T1. Let's go ahead and find it. We're going to use this same function. Okay. But now we're going 30 degrees. 30 degrees is equal to pi over 6. Starts from 0. 1/2. And then using the same acceleration. Okay. Okay. Square root. Okay, so what we found was the time it takes to get to 30, because it's asking us for this time. So we found this time right here, 0.41. We know total time 0.59, so that's why we subtract. So 0.59, 0.41. Alright, you get T2 is equal to 0.18 seconds. Okay, on to the last part. Part J wants us to calculate the total change in angular momentum of the rod about the pivot from 60 to 0. Okay, so change in L is equal to LF minus LI. Now, there is no LI because it starts from rest. So that means change, or delta change, something. Delta L is equal to delta, or LF. Alright. So now we just expand. L is equal to I omega, and this is LF, so omega F. I for rod, 1/3 ml squared. And we need to find omega. So I'm going to use the final omega function. And we are going to use the acceleration we found and total time, because this is final omega. So total time that we just found, there is no omega I. So we can go ahead and plug the omega F we just found. Okay. Now we just plug in everything we know. and units. Alright, and that is your Newton's change in angular momentum. And that concludes FRQ number 3.